welcome back to the Deep Dive. All right, today we're diving into a topic that, well, it touches pretty much everyone, one way or another. It's one of the toughest health challenges humanity faces. Cancer.
It really is.
Yeah.
Incredibly complex, relentless, and, for a long time, our methods for fighting it haven't been quite as effective as we all hoped.
Yeah. So we're pulling insights today from Chapter 8 of a book that takes a really hard look at how we approach health and specifically how we approach cancer.
Right.
Our mission in this deep dive is to get to the heart of why cancer is so deadly, explore some of the surprising limitations of, let's say, traditional approaches, and most importantly, uncover the new strategies in prevention, treatment, and especially early detection that are finally starting to offer some real hope.
Cancer is tragically the second leading cause of death. It's a disease we actually declared war on back in, 1971,
Right.
with this massive national effort.
Yeah, I remember that. The hope then was that we'd have it largely conquered within 5 years, wasn't it?
That was the idea. And, 50 years later, that hasn't quite panned out. It's pretty sobering when you realize that while mortality rates for something like heart disease have dropped dramatically, cancer mortality rates in the U.S. are stubbornly similar to what they were when that war on cancer started. Now, we've had incredible wins against specific cancers, absolutely, especially in kids.
True.
But the overall picture remains, challenging.
It's definitely seen as a disease of aging, right? Becomes far more common as we get older.
It does, but what's also striking is how significant a killer it is in middle age. The chapter points out that back in 2017, more people between 45 and 64 died from cancer than from heart disease, liver disease, and stroke combined in that age group.
Wow, combined.
Combined. And when it strikes then, it's often caught at a later stage, which is part of the problem.
So the book really lays out two major problems contributing to this difficult fight. What are they?
Well, the first big hurdle is that once cancer is established, especially if it's spread, metastasized, it's incredibly difficult to treat effectively with our current tools.
Right.
The second, and arguably even bigger problem right now, is that our ability to detect cancer at a truly early stage is still pretty weak across most cancer types.
That really sets the stage. And the chapter opens with this amazing, almost kind of mysterious story from 1968 that perfectly illustrates those early glimmers of hope against this backdrop of difficulty.
Oh, yeah. The case of James D'Angelo. He was in his 60s, diagnosed with metastatic stomach cancer 12 years before. The doctors at the time had removed the primary tumor but found it had spread to his liver.
Which was basically a death sentence back then.
Absolutely. They just sent him home, expected him to die.
Presumed terminal.
Exactly. But 12 years later, he comes back for routine gallbladder surgery. And the young resident on the case, Steve Rosenberg, goes in expecting to find his liver just riddled with tumors, or at least evidence of them, but nothing. Absolutely no sign of the metastatic tumors in his liver. They were just gone.
Wow. Just vanished.
Vanished. This was, almost unheard of. Only like 4 reported cases of spontaneous remission of metastatic stomach cancer in medical history up to that point.
Incredible.
And for Rosenberg, it sparked this profound question. How? How could this happen? His hypothesis was that D'Angelo's own immune system must have somehow recognized and destroyed the cancer cells, like the body fighting off an infection, but turning its power onto this rogue self.
Which was a totally radical idea in medicine at the time, wasn't it?
Completely countercultural. But it became Rosenberg's life's work. He dedicated his entire career to trying to figure out how to harness the immune system against cancer. And for decades, it was incredibly challenging, often marked by, a lot of failure in the early years.
It's powerful how these fights against disease are so personal. The author also shares how volunteering in a pediatric cancer ward deeply affected him and shifted his focus from engineering to medicine. Seeing that struggle up close, especially with kids, it just brings home the urgency, doesn't it?
It really underscores what's at stake. And despite decades of effort and, incredible investment since that 1971 declaration, that overall mortality rate just hasn't budged the way we hoped.
So traditional treatments, surgery, radiation, they work for local tumors.
They're vital for local tumors, yes.
Yeah.
But they hit their limits once the cancer spreads, once it metastasizes.
And chemo, what's the story there?
Chemotherapy is systemic, so it can reach metastatic cancer cells throughout the body.
Right.
but it's often not curative, and it comes with brutal side effects because it's just not specific enough.
Right, it hits everything that divides fast.
Exactly. It kills rapidly dividing cells,
Yep.
which cancer cells are, but also lots of your healthy cells, hair follicles, gut lining, immune cells. The chapter quotes Christopher Hitchens describing just how horrific it was,
Yeah, that was powerful.
questioning if he would have even chosen that path knowing the reality. And worse, cancer cells can evolve resistance to chemo, kind of like bacteria developing resistance to antibiotics.
So the real challenge is finding something that's systemic and truly specific to the cancer cells. And to do that, we need a deeper understanding of what makes a cancer cell tick, what makes it vulnerable.
Precisely. What really defines cancer? It's not necessarily that they grow faster than normal cells, sometimes they don't. The key is they ignore the signals that tell them to stop growing or to die. They just keep dividing unchecked, driven by accumulated genetic mutations.
And their other defining, really terrifying characteristic.
Their ability to metastasize, to break away from the primary tumor, invade blood vessels or lymph channels, travel through the body, and then seed new tumors in distant organs. This is the transition from a local problem you might just cut out to a systemic disease that's incredibly hard to eradicate. And, metastasis is responsible for about 90% of cancer deaths.
90%. And yet the chapter points out that a surprisingly small amount of cancer research funding specifically targets metastasis. That seems like a huge mismatch.
It really does. Part of the challenge is also just the sheer diversity of cancer itself. The Cancer Genome Atlas Project, which sequenced thousands of tumors, showed just how incredibly complex it is.
Right. The initial hope was that sequencing would reveal a few key drivers for each cancer type that we could target easily.
Find the perfect drug for the specific mutation, yeah. But what they actually found was tumors had hundreds, sometimes thousands, of mutations, many of which seems like random passenger mutations, not drivers. Even two breast cancers from different people could be genetically vastly different. It made the idea of a single genetic cure for breast cancer seem, well, less likely, at least based purely on those initial genetic findings.
It sounds like trying to find one magic bullet when it's more like facing a whole army with different armor.
That's a good analogy.
Right.
But this deeper understanding of cancer has revealed some systemic weaknesses that are more universally targetable. The chapter focuses on two really key hallmarks identified by researchers like Hanahan and Weinberg. One is altered metabolism, and the other is the ability to evade the immune system.
Okay.
These aren't single mutations, but fundamental properties cancer cells acquire to survive and spread. And these offer more systemic targets.
Okay, let's unpack those. First, cancer metabolism. This takes us back to the 1920s, right? Otto Warburg.
Yeah, Warburg noticed that cancer cells were basically glucose hogs. They just devoured glucose at an incredibly high rate compared to healthy cells. But even when there was plenty of oxygen around, they preferred this really inefficient energy pathway, fermentation, which produces lactic acid.
The Warburg effect. And that's still used today, isn't it? That's why PE scans light up tumors or sucking up all that radioactive glucose.
Exactly. That's precisely how PT scans work. Now, Warburg thought this inefficiency was the key, maybe even a cause of cancer. But the modern understanding, spearheaded by scientists like Luke Cantley, Matthew Vanderheit, and Craig Thompson, it's different.
How so?
They argue the inefficiency isn't really the goal. This pathway, while it's not great at making immediate energy, ATP, it's incredibly effective at generating something else.
Which is?
Building blocks. The raw materials needed for rapidly dividing cells to construct new proteins, lipids, DNA. So the Warburg effect fuels cancer cell proliferation by providing these components.
Oh, okay.
And that becomes a potential vulnerability.
And this connects directly to our own metabolic health. This is fascinating.
Absolutely. This metabolic pathway is strongly influenced by signals like insulin and IGF-1, which are growth factors. So if you have chronically elevated insulin and IGF-1 levels, which is common in conditions like insulin resistance, prediabetes, type 2 diabetes,
You're basically pouring fuel on the fire.
you're essentially drenching these pathways in growth signals. So obesity and type 2 diabetes aren't just risk factors because of inflammation, although that plays a role. High insulin itself can act as a potent cancer enabler.
Wow.
This is where, the low-hanging fruit comes in. While we can't avoid all mutations, we can work on improving our metabolic health, lowering insulin and IGF-1 levels through things like diet and exercise. It's not a cure, but it's a powerful strategy to reduce risk and potentially slow down existing cancer by removing some of its fuel source.
And these insights are actually translating into new treatments now. Cantley's work on the PI3K pathway, which is downstream of insulin signaling, that led to targeted inhibitors.
Yes, drugs targeting PI3K were developed, but they had kind of mixed success and this really frustrating side effect. They often raised blood glucose and insulin levels.
Oh, no.
Yeah, potentially stimulating the very pathways the drug was trying to inhibit. Kind of counterproductive.
This is where that personal story about Sandra in the chapter is so striking, isn't it?
It really is. She had metastatic breast cancer, was in a trial for one of these PI3K inhibitors.
Yeah.
But alongside the drug, she adopted this very strict low-insulin diet.
Okay.
And while everyone else on the trial at her site eventually succumbed to the cancer, she survived for years. Now, it's anecdotal, of course, but it sparked a crucial idea.
That maybe combining approaches is key, stacking therapies.
Exactly. It actually inspired the Mukherjee-Cantley mouse study mentioned in the book. They took mice with human tumors and combined a ketogenic diet, which lowers insulin, with a PI3K inhibitor. The combination was dramatically more effective than either therapy alone. It's a powerful illustration of how influencing the tumor's metabolic environment can potentially enhance targeted drug therapy.
Like using diet to make the cancer more vulnerable to the drug. That makes sense. And what about Walter Longo's work on fasting? That seems so counterintuitive when people are going through harsh treatments.
It really does. Because the traditional advice during chemo is often just eat whatever you can, keep your weight up. But Longo's work suggests that fasting, or these fasting mimicking diets, might actually make healthy cells more resistant to chemo's damage.
Oh, interesting.
While making cancer cells more susceptible. The thinking is that stressed cancer cells can't hunker down and protect themselves like healthy cells can when nutrients are scarce. Studies suggest it's safe for chemo patients and might even improve outcomes and reduce side effects. Again, lowering insulin seems to play a role there too.
So attacking cancer's metabolism and using metabolic strategies as helpers, essentially. Really powerful stuff. Now let's jump to that other big hallmark, evading the immune system. Back to Steve Rosenberg's quest.
Right. So the immune system is brilliant at killing foreign invaders like bacteria or viruses. But cancer is tricky because it arises from our own cells, its mutated self. And it evolves these clever mechanisms to essentially hide from or switch off the T cells, which are the immune system's main killer cells. Immunotherapy aims to reverse that, to unmask the cancer and train or unleash the T cells to recognize and attack these rogue cells.
Like William Coley's really early controversial work trying to use bacterial infections to stir up the immune system against tumors.
Exactly, that was the early intuition. And Rosenberg's early work with IL-2, remember Linda Taylor, while it was highly toxic and only worked in a small fraction of patients, it was proof of principle. It showed the immune system could be roused to fight cancer effectively, at least sometimes.
But the real revolution came more recently, right? With things like RT cells and checkpoint inhibitors.
Definitely. CAR-T therapy is amazing, but it's very specific. You take a patient's T cells out, you genetically engineer them in the lab to recognize a very specific target marker on the cancer cell, like CD19, on certain types of lymphoma. You grow billions of these super soldier T cells, and then you infuse them back into the patient. It works incredibly well for some blood cancers by basically wiping out all cells that have that specific marker. The challenge is finding such universally expressed, unique markers on other solid tumor types.
Right, and checkpoint inhibitors. This is the Nobel Prize-winning work of James Allison and Tasuku Honjo. How does that work?
Their approach is different and really clever. Instead of engineering T cells to find the cancer, they block the signals that cancer cells use to turn off the T cells that might already be there. Think of T cells as cars, ready to attack, but the cancer cells are stepping on the brakes. They use molecules like CTLA-4 or PD-1. These checkpoints are normally safety switches in the immune system to stop it from attacking healthy tissues.
Okay, so they're normal parts of the system.
Yes, but cancer cells hijack them. They exploit these brakes to evade detection. Checkpoint inhibitors basically block those brakes, release them.
So the T cells, which might already recognize the cancer but were being suppressed, are suddenly unleashed to do their job?
Precisely. And the results, when they work, can be absolutely stunning, like former President Jimmy Carter's metastatic melanoma just disappearing after treatment with a PD-1 inhibitor.
Incredible story.
Or the powerful story of your friend Michael, mentioned in the book, who had notoriously deadly pancreatic cancer linked to Lynch syndrome.
A type of cancer that is usually just a death sentence very quickly.
Completely. Surgery wasn't even an option. But because his cancer had a specific genetic signature, high microsatellite instability, linked to his Lynch syndrome, he was a candidate for a checkpoint inhibitor, Keytruda. And amazingly, it worked. His immune system eradicated the tumor.
An absolutely incredible success story, but it came with a significant cost in his case, right? His pancreas was essentially destroyed in the process, leading to type 1 diabetes.
A very high price, yes, but he is alive and healthy years later, able to see his children grow up, which simply wouldn't have been possible otherwise. These stories really highlight both the incredible potential and sometimes the significant trade-offs involved.
Yeah, and the chapter notes that these therapies only benefit a relatively small percentage of patients so far. That's important context.
It is. But, and this is the critical point, for those patients they do work for completely, the results are often transformative and incredibly long-term.
That's the real game changer.
While it's not a universal cure yet, for the patients who are complete responders, the remissions are often essentially permanent. We're talking 80–90% disease-free survival at 15 years in some studies for metastatic disease. That was unheard of previously.
Wow.
So, making this work for more patients, maybe combining it with other therapies like chemo to make the cancer more visible to the immune system, that's the cutting edge right now.
And there's one more technique mentioned, adoptive cell therapy, or ACT. What's that?
ACT is fascinating.
Yeah.
It's kind of like sending in a custom-trained army of T cells. You take a patient's T cells, either those that have already infiltrated the tumor, called TILs, tumor-infiltrating lymphocytes, that might have some natural recognition, or you take T cells from their blood and genetically engineer them, similar to ART, to specifically target the cancer. Then you grow these selected or engineered cells in the lab, multiplying them into the billions, and infuse them back into the patient.
So you're just overwhelming the tumor with sheer numbers of targeted killers.
Exactly. It's highly personalized, it's complex, and currently very expensive. But the results in some trials, especially with TILs for melanoma, are extremely promising, again, with the potential for very durable long-term remissions. This whole area, metabolism, immunotherapy, ACT, is where the real hope for future treatments lies.
Okay, so we've explored the history, the biology, these exciting new frontiers in targeting metabolism and unleashing the immune system. But the chapter makes this really compelling argument that the single most powerful tool we have against cancer today isn't some new drug or high-tech therapy, it's something simpler.
Early detection, yeah. This is probably the most crucial takeaway that can impact everyone right now. The statistics are just stark. 10-year survival for most metastatic cancers is sadly close to zero.
Devastating.
But if you catch that same cancer early, when the tumor is small, localized, hasn't spread, has fewer cells, fewer accumulated mutations, the survival rates just skyrocket.
It's a numbers game, right, and a mutation game. A smaller tumor means fewer cells to kill and much less chance they've evolved resistance to whatever treatments you throw at them.
Exactly. Look at colorectal cancer, for example. Metastatic CRC survival with modern chemo might give you a median of 30 months, but effectively zero 10-year survival.
Right.
But if you catch it at stage 3 after surgery to remove the primary tumor, and you treat with that same chemo regimen as adjuvant therapy, the 10-year survival jumps to something like 67%.
Huge difference.
Or HER2 positive breast cancer. Metastatic survival is under 5 years median. Catch it early, remove it surgically, treat with adjuvant therapy like Herceptin. 7-year disease-free survival is 93%. The difference catching it early makes is just immense.
And yet, reliable screening only exists for a handful of cancers. That's the frustrating part.
It is. And historically, the Medicine 2.0 approach has been very cautious, heavily weighing the risks of false positives, unnecessary biopsies, anxiety, costs.
Understandable concerns.
Understandable, but it has sometimes limited the uptake and recommendation of even the screening we do have. The perspective shifts in Medicine 3.0, as the book calls it. Screening tools aren't perfect, no, but they are incredibly powerful instruments that we need to learn to refine and use strategically.
Absolutely. It's about understanding the trade-offs, isn't it? Sensitivity catching the cancer if it's there versus specificity correctly identifying someone without cancer.
Exactly. And prevalence matters too. If you screen a very low-risk population, yeah, most positive results might be false positives. But for cancer, where missing it has such catastrophic consequences, that balance needs really careful consideration, especially in higher-risk individuals or as people get older.
So how do we make detection better? What are the strategies?
Well, one way is stacking modalities. Instead of just mammography, maybe adding ultrasound or even MRI for women at higher risk or with dense breasts. For prostate cancer, moving beyond just a simple PSA number.
Right. That's controversial.
To look at things like PSA velocity, Density, the ratio of free to total PSA, combining it with other tests like the 4K score, and using multiparametric MRI to better distinguish those slow-growing cancers unlikely to cause harm, the ones men might die with, rather than from the aggressive ones that really need treatment.
Makes sense. And the colonoscopy gets really high praise in the chapter.
Oh, it's an amazing tool because it's not just screening, it's actually prevention. You can visualize polyps, these precancerous lesions that almost all colorectal cancers develop from, and you can remove them right then and there before they ever turn into cancer.
Stopping it before it starts.
Exactly. It's incredibly effective.
And the chapter argues pretty strongly for screening earlier than the standard age 45 or 50, suggesting maybe age 40 or even earlier for some people.
Yeah, given that a significant number of younger people diagnosed with colorectal cancer have no family history, and polyps can sometimes progress relatively quickly, waiting till 45 or 50 seems, well, questionable when earlier detection offers such a huge survival advantage. It's an asymmetric risk calculation, isn't it? The potential harm of a missed cancer is just immense, while the risks and costs of screening, though real, are generally far lower. And colon cancer is particularly targetable because it's accessible via colonoscopy.
What about other methods? You mentioned visual checks, imaging.
Yeah, visual exams for things like skin cancer or cervical cancer using pap smears are crucial and effective. Imaging like low-dose CT scans for lung cancer in current or former heavy smokers is standard practice now, but research is ongoing for other groups too. MRI is very powerful. The chapter mentions DWI MRI. Diffusion-weighted imaging is a promising lump finder. It's highly sensitive, it finds lots of things, but it has lower specificity, meaning it finds lots of lumps, most of which turn out not to be cancer. So it definitely needs other tests alongside it to figure out what's actually concerning.
Right. And finally, the technology that feels potentially revolutionary, liquid biopsies.
Ah, yes. This is where the future of early detection could be radically different. The idea is detecting cell-free DNA, these tiny fragments of DNA shed by cells, including cancer cells, into the bloodstream.
Okay.
It's already being used effectively to monitor for recurrence in patients who are known to have had cancer, where you know the specific mutations to look for. But the real game changer is using it for multi-cancer early detection in apparently healthy people.
So looking for cancer when you have absolutely no reason to suspect it, that sounds incredibly hard, like finding a needle in a haystack.
It is incredibly hard. You're looking for a minuscule signal amidst a vast amount of background noise from normal cell turnover. Tests like the Gallery test from a company called Grail are pioneering this. They don't just look for specific mutations, which might be rare. They look at methylation patterns on the cfDNA.
Methylation, like chemical tags on the DNA.
Exactly. Think of them as chemical tags or annotations on the DNA that can signal if the DNA likely came from a cancer cell and potentially even what type of tissue it originated from. It's looking for a specific epigenetic fingerprint.
Okay, so it's a different kind of signal. And how well does it work?
Well, initial studies show it has quite high specificity, meaning if the test flags you as potentially having cancer somewhere, there's a pretty good chance you actually do. False positives seem relatively low. The sensitivity, its ability to pick up cancer when it is present, varies. It seems better right now at finding more aggressive, perhaps slightly later stage cancers that shed more DNA into the blood, but it's also detecting some earlier stage cancers too.
And the real potential here is detecting cancers before they're large enough to be seen on imaging, like a CT scan or an MRI.
That's the seismic implication the book talks about. That's the dream. If we can reliably find microscopic or very small localized cancers through a blood test, intervention becomes possible when the cancer is far more manageable, potentially even completely eradicable with less aggressive treatments. It could fundamentally flip the timeline of cancer diagnosis.
Stepping back then, this whole deep dive really reinforces that cancer is, well, a formidable adversary, a very difficult horseman, as the book frames it. And there's an element of just bad luck involved, isn't there? Random mutations we can't entirely control.
Definitely. There's an unavoidable stochastic element. And while our current tools for treatment and prevention aren't yet as universally effective as, say, statins for heart disease or managing blood sugar for metabolic syndrome, we do have crucial modifiable risks we absolutely should focus on.
Right.
Smoking, obviously, is the big one. But increasingly, managing insulin resistance, obesity, overall metabolic health, that's emerging as maybe the second most important modifiable factor.
But the hope, it feels more tangible now than it has in decades, wouldn't you say? This dual front of exciting new targeted therapies, particularly immunotherapy, which offers the possibility of genuine long-term survival for some patients where none existed before, combined with this rapidly advancing field of early detection technology.
Absolutely. Catch it as soon as possible becomes the most actionable and powerful strategy we have right now for almost everyone. It does require a shift in mindset, perhaps embracing more proactive screening strategically, despite the complexities and the need for better tests.
Yeah.
Because the cost of missing an early treatable cancer is just so incredibly profound.
Weighing those personal costs, societal costs, the anxiety of false positives against the devastation of a late-stage diagnosis. It's complex, for sure, but the evidence really points towards the immense value of finding cancer earlier.
And for the first time, really, the vision of cancer becoming not necessarily extinct maybe, but perhaps a manageable chronic disease for many detected early, treated effectively, maybe no longer qualifying as one of those ultimate horsemen. That vision feels within reach.
Yeah.
It's not science fiction anymore. It feels like a realistic possibility being driven forward by relentless research and incredible technological advancement.
It's a powerful message of both, the ongoing challenge, but also genuine, tangible hope. This deep dive really clarified the landscape of the fight against cancer, understanding its fundamental nature, the promise of these new therapies targeting metabolism and the immune system, and just the transformative potential of finding it early.
It's definitely a long fight still, but the progress in these areas is undeniable and offers significant hope for the future, much more so than even 10 or 20 years ago.
Absolutely. Well, a big thank you for guiding us through this incredibly important and complex topic.
My pleasure.
And thank you for joining us on this deep dive into the fight against cancer.
We really hope this provides a clearer picture of both the challenges and the truly exciting progress being made, and maybe inspires you to think about the importance of metabolic health and strategic early screening in your own life.
That's a wrap for this deep dive. We'll see you on the next one.